Hi, myself S. Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. In this lecture, we are going to discuss definitions and terminology on CPU and computer arithmetic. So, the instruction. So, let's start with the definition of the instruction. So, instruction is a command to the processor to perform a specific task. So, in a computer, it works according to the instructions. So, instruction means it is a command to the processor to perform a specific task. So, that is the instruction. So, these instructions, they are classified into different categories. So, the basic computer has a 16-bit instruction register, which can denote either memory reference or register reference or input or output instruction. So basically, when you write any program, the program is stored in the memory. So from the memory, the instructions are fetched. Once the instruction is fetched from the memory, then the instruction is placed in the instruction register. So the size of the instruction register is a 16-bit. So fetching means retrieving the instruction from the memory. So once the instruction is retrieved from the memory, then it will be placed in the 16-bit instruction register. So these instructions mainly, they are classified into three types. The first one is the memory reference instruction. Next one, register reference instruction. And third one is the input or output instruction. So coming to the memory reference instruction. So the memory reference instruction refers to the memory address as an operand. Okay, so in order to get the operand, we are referring to the memory address. So using that memory address, we are accessing that particular operand. Operand is nothing but the data. So the other operand is always the accumulator. So if you want to perform any operation, okay, so we require two values. So here in this scenario, one value is stored in the accumulator and another value is a reference to the memory. So the instruction register format. So this is a instruction register format, instruction format. This is a format of the instruction. So total the instruction size is a 16-bit. So 0 to 11, it represents the address, memory address, in order to get the operand. And 12 to 14 bits, it represents the opcode. So opcode means operational code. It specifies what type of operation it has to be performed. And 15th bit, it specifies whether the instruction is having direct address or indirect address. If I is equal to 1, then it is a indirect address. If the I is equal to 0, then it is a direct address. So here in this, so the opcode bits are 12, 13, 14. So using these 3 bits, we can decode 2 power 3 combinations. That means we can have 2 power 3 combinations. That means 8 combinations we can have. So the starting with 0, 0, 0, next 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. So total we have 8 values. So starting with 0 to 7. So this 0 to 6 are the memory reference instructions. 0 to 6 are the memory reference instructions. So when the D7, so D7 means the bits of opcode bits of 12, 13, 14 are all ones. So when all opcode bits are equal to 1, then it classified as it may register reference instruction or IO reference instruction. Okay, coming to the register reference instruction. So these instructions perform operations on registers rather than memory address. So here the instruction register 12 to 14 is a 111. So from 000 to 110. So for this, so total 7. So for all these are memory reference instructions. Memory reference instructions. So when the combination, when the opcode bits are 12, 13, 14 bits are 111, then it may be a register reference instruction or IO reference instruction. Okay. So then see here. So for the register reference instruction, the opcode bits are all ones and the 15th bit, that is a I bit is equal to 0. So for this combination, it is a register reference instructions. And the 0 to 11, it represents the register operation. Okay. So based on the this 15th bit, we can differentiate the register reference instruction from the IO reference instruction. So if the 15th bit is equal to 0, then that is a register reference instruction, and if 15th bit is equal to 1, then that is a IO reference instruction. So in this scenario, input or output reference instruction, so we have 12, 13, 14 bits are 1, 1, 1, and 15th bit is a 1. So it represents the 15th bit 1, it represents that it is a input or output reference instruction. And 0 to 11 bits represents that particular input or output operation. And coming to the instruction cycle. So when we write any program, that will be stored in the memory. So program is nothing but a collection of instructions. So the program is residing in memory unit of a computer, consists of sequence of instructions. So program is nothing but a sequence of instructions, and these instructions are executed by the processor by going through the cycle for each instruction. So for execution of the instruction, the instructions are executed by the processor by going through the cycle for each instruction. So that means every instruction, it has to undergo through a cycle in order to execute. That cycle is called instruction cycle. So the definition of the instruction cycle is the time taken by the instruction in order to undergo the fetch, decode and execute. That is called instruction cycle. So this instruction cycle, it can also called fetch, decode, execute cycle, because every instruction, it has to undergo through all these three phases. So the first phase is the fetching, and the second one is the decoding, and then executing. So if the first instruction fetched, decoded, executed, then only the second instruction will be fetched from the memory. So in this way, all the instructions of the program gets executed. So it is a basic operational process of a computer, in which a computer retrieves a program instruction from its memory that determines what actions the instruction dictates and carries out those actions. So fetching means it is a retrieving from the memory. Then decoding means converting the human understandable language to the machine understandable language. Then execution means performing or implementing those operations. And these are the different phases of the instruction cycle. So first phase is fetching. So fetching means reading the instruction from the memory into the processor. So fetching means reading or retrieving an instruction from the memory. Because see, so in a memory, we have multiple memory locations. So in that memory locations, these instructions will be stored. Let us assume I1 instruction. So first instruction is stored in the memory. Then I2, I3. So these are all the different instructions. So first the instruction 1 will be fetched from the memory. After fetching, then decoding. So decoding means in general we will write the program using some high level language or assembly language. Okay, so as a human we can understand the high level language or high level language or assembly language, but the machine cannot understand this high level language and assembly language, because the machine can understand only the machine language, that is nothing but the binary language, zeros and ones. So that's why in the decoding phase it will converts the human understandable language into the machine understandable language. Then it interpret the operation to be performed. And also in the decoding phase, it will calculate the effective address. It calculates the effective address. Effective address means it is the address of the operand, where the operand is present in the memory. And then after decoding, if the instruction is having indirect addressing, then read the effective address from memory if the instruction has an indirect address. Then the last phase is the execute. So executing means interpreting the opcode and performing the dictated operation. So that means suppose if you have a instruction add a comma b. So add means addition. So the CPU has to perform addition operation. So that means in the execution phase it will implement this addition operation. So these are the various phases of the instruction cycle. So you can see the instruction cycle in a graphical representation. First one is a fetch instruction, then decode, read the address from the memory, then execute the instruction. So if the first instruction completed fetching, decoding and execution, then the second instruction will be starts fetching the instruction from the memory, then decoding, then executing. So in this way, all these three phases will be executed, performed. And if you go in detail about the instruction fetching, so in this instruction fetching, the program counter, it plays a vital role. Okay, so what is a program counter? So the definition of the program counter is it is a register. So a register is nothing but a collection of flip-flops. Flip-flop is nothing but it is a single bit storage device. That means using single flip-flop we can store either 0 or 1. So this program counter which stores the address of the next instruction is to be executed. So that is the purpose of the using program counter. So if you have memory, here in the first memory location, we have a instruction I1, then I2, instruction 2, instruction 3, instruction 4, and so on. Let us assume the first instruction is stored at address 4000. Next address is 4001, 4002, 4003, and so on. So when the first instruction is executing, that means the first instruction is located at memory address 4000. So the next instruction I2, it is located at the memory address 4001. So this the address of the next instruction is stored in program counter. So that means the program counter which stores the address of the next instruction. Okay. Hence, depending upon the value of PC address, it's sent through address bus to the memory, and then specific instruction is sent back through the data bus. So this is how the instruction is fetching from the memory. So here program counter is there. So here 1000. So this address information, it is sent to the memory through the address bus, because in order to send the address, we are using address bus. So through that address bus, we are sending address information to the memory. Then in that particular address, we will have a instruction. So that instruction will be retrieved, and that retrieved instruction is sent to the instruction register, because once the instruction is retrieved from the memory, then immediately it will be placed in the instruction register. So this is the instruction register. So once the instruction is retrieved from the memory, then it will be stored in the instruction register by sending through the data bus. So this is a process of instruction fetching. And coming to the instruction decoding. So after fetching an instruction, the next phase is the decoding. So decoding means conversion of the user-friendly language to the machine language, because we will write the program using some high-level language, nothing but using some English words, or using some assembly language like some add a comma b, increment a, and so on. So as a human, we can understand this assembly language and high-level language, but machine cannot understand. So that's why we are converting the human understandable language into the machine understandable language. And coming to the instruction execution. So instruction execution is once the instruction gets decoded, the processor executes the instruction. In this phase, the processor performs the actions specified by the given instruction. So suppose if you have add a comma b. So here in this is a opcode. That means that is the action to be performed. So in this instruction execution phase, this particular action will be implemented. That means the CPU will perform addition operation on the data present in the register B and the register A. So according to this, add the contents of B register is added with the contents of the A register. Once added, the result will be stored in the accumulator. So A plus B will be stored into A. And coming to the registers. So in a CPU, in a central processing unit, we have several registers. So the first one is the program counter. So already we have seen just before the definition of the program counter. So program counter is a register that holds the address of the next instruction is to be executed. It holds the address of the next instruction is to be executed. Next one, memory address register. Memory address register. So this memory address register, it holds the address of a block of memory for reading from or writing to. So you can understand with this, it is a memory, consists of several memory locations, and instruction, first instruction I1, I2, second instruction, then I3, I4, then address 4000, 4001, 4002, 4003. So these are here in this scenario, 4 instructions are stored in the memory and corresponding memory addresses. So when the first instruction is executing, then the corresponding address will be the 4000. So this is a current address of the currently executing instruction. So this memory address register, it holds the address of the block of memory for reading from or writing to. So that means it holds the starting address of the memory block for reading from or writing to. Then one, next one is a memory data register. So it is a two-way register that holds the data fetched from memory or data waiting to be stored in the memory. So this memory data register, it can be used as a two-way. That means suppose if you want to store the data to the memory, so then the data we can store in the memory data register, or once the data is retrieved from the memory, then that retrieved data can be placed in this memory data register. So either way we can use this memory data register. And next one is a instruction register. So instruction register is a temporary holding for the instruction that has just been fetched from the memory. So once the instruction is fetched from the memory, then this instruction is placed in the instruction register. So all the fetched instructions are stored in the instruction register one by one. And then next one is the control unit. So this control unit, it decodes the program instruction in the IARE, selecting the machine resources such as data source register and a particular arithmetic operation, and coordinates activation of those resources. And mainly the control unit is present in the central processing unit, and it is responsible for generating the various timing and control signals. And next one is the arithmetic and logic unit. So this arithmetic and logic unit, it is plays a important role in the central processing unit because it performs various arithmetic operations like addition, subtraction, multiplication, division, and so on. Similarly, it also performs some logic operations such as and, or, XOR, not, complementing, clear. So these are all the various arithmetic and logic operations performed by this ALU. And data representation. So data representation, it refers to the manner in which the data is stored in computer. So that is called data representation. So data representation means the manner in which data is stored in the computer. So binary information is in digital computer is stored in processor registers or the memory. So always in the processor registers or memory, we are storing the binary data. So these registers, it may contain two types of, it may contain either data or the control information. So data is nothing but the numbers and the other binary coded information that are operated on to achieve required computational results. And the control information is a bit. It is the control information. It could be a single bit or a group of bits used to specify the sequence of command signals needed for manipulation of data in other registers. And coming to the number system. So number system is simply a system to represent or express numbers. So the definition of number system is simply a system to represent numbers, to represent or express the numbers. Okay. So in a computer system, we have several number systems that are binary number system, octal number system, decimal number system, hexadecimal number system. So in binary number system, we have only either 0 or 1. So we have only two values, two set of values. One is 0 and another one is a 1. And second one is a octal number system. So in octal number system, we have the numbers 0 to 7. So the base or radix of the octal number system is 8. And the base or radix for the binary number system is 2. That means only two numbers are available, that are 0 and 1. Whereas in octal number system, the base is 8. That means from 0 to 7 numbers are present. and decimal numbers. So the base of the decimal number system is 10. So that means the decimal numbers are from 0 to 9. And similarly, hexadecimal number system, the base is the 16. So the numbers are from 0 to 9 and the alphabets A to F. So A corresponding to the 10, P corresponding to 11, 12, 13, 14, 15. So F corresponding to 15. So these are the various number systems in the computer. First one is a binary number system. Okay, so in binary number system only we have zeros and ones. So this is a binary number system. So that means it consists of only the ones and zeros. So for example, 110101 is a binary number. We can convert any number system to the binary and vice versa. So if any number is there, that can be converted into the binary. Suppose if we have a decimal number 14. So decimal number is a 14. That we can convert into the binary. So by dividing the decimal number with 2. So if you divide the decimal number with 2, 2 sevens are 14. So the remainder is a 0. And again we are dividing with 2. 2 threes are 6. And the remainder is 1. And 2 ones are 2. Remainder is a 1. So after division, we have to take the remainders from the bottom to top. So that means 1, 1, 1, 0. So this is a equivalent binary number corresponding to the 14 in decimal. And next one is a octal number system. So in the octal number system, the base is 8 and the numbers are from 0 to 7. So here one octal number is given that we are converting into the decimal. So for that we need to convert like this. So 8 power 0, 8 power 1, 8 power 2. So that means the hundreds position is multiplied with 8 power 2. We have to write like 8 power 0, 8 power 1. So that means the weight of the 0th position is 8 power 0. The weight of the first position, 10th position is 8 power 1. The weight of the 100th position is 8 power 2. So we can write 2 into 8 square plus 1 into 8 power 1 plus 5 into 8 power 0. So 2 into 8 square, 8 into 8, 64 plus 1 into 8 plus 5 into 8 power 0, 1. So 2 into 64, 128, 1 into 8, 8, 5 into 1, 5. So total you will get 141. So in this way any number can be converted into the decimal. And coming to the decimal number system. So in decimal number system the base is 10 and the numbers are from 0 to 9. Okay. So here we have a decimal number and that we can convert into the decimal. So this is a decimal number. So how this we can represent? So this is we can write 10 power 0, 10 power 1, 10 power 2, 10 power 3. So 1 into 10 power 3, 1000. 1000. So 4 into 10 square, 400. 5 into 10 power 1, 50. 7 into 10 power 0, 7. So total 1457. And coming to the hexadecimal number system. So hexadecimal number system, the base is 16 and its numbers are from 0 to 9 and A to F. So these are the hexadecimal numbers. So here you can see. So 0 to 9 and A to F. And corresponding decimal numbers are 0 to 9. So 0 to 9 or representation is same in both decimal as well as hexadecimal. But from the 10th onwards, it is different. So 10 in the decimal, that is corresponding to the A in the hexadecimal. 11 in decimal is corresponding to B in hexadecimal. So and so on up to the 15. So 15 in decimal number is corresponding to F in hexadecimal. And coming to the addressing modes. So the term addressing mode, it refers to the way in which operand of an instruction is specified. Okay. So addressing mode means the way in which the operand of an instruction is specified. So that means we can specify the operand in several ways. That means we can specify the operand in a directly in the instruction, or we can specify the operand in the register, or we can specify the operand in the memory. Okay, so these are the different ways to specify the operand. So this addressing mode will specifies how the operand is specified in the instruction. So for that purpose, we have several addressing modes. So the assembly language program instruction consists of two parts. So every instruction mainly it consists of two parts. The first one is the opcode and the second one is the operand. So opcode is the operational code which specifies what type of operation it has to be performed. And operand is nothing but the data on which we are performing that particular operation. So example, add A comma B. So add is a opcode and A comma B are the operand. That means we are performing addition, add operation on the operands stored in the register B and the register A. And coming to the types of addressing modes. So already just before we have seen the definition of addressing mode. Addressing mode refers to the manner in which the operand of the instruction is specified. Okay, so first one is a implied mode, implied addressing mode. So in implied addressing mode, the operand is specified as part of the instruction. Example, CLA, clear accumulator. That means the operand is stored in the accumulator and that accumulator is part of the instruction. And second one is a immediate addressing mode. So in immediate addressing mode, the operand is specified in the instruction directly. So in the address field, they have represented the operand. So that means hash represents immediate operand. So that means 35 is the immediate operand or immediate data. Register direct. So in register direct addressing mode, the operand is specified in the register. So here, operand is specified in the register. Suppose if the CX is equal to 35, that means 35 is the operand. That 35 we are moving to the register AX. Register indirect. Register indirect. So this is a register indirect mode. That means the operand is not given in the not given directly in the register. So the indirect operand is given in a indirect way. Suppose if BX is equal to 4000. So we have a memory. Four 000. Okay, so the 4000 is not the operand, it is the address. So in that address it stores the address of the operand. So if we go to this address 4000, again we have a 4500. So from this it will comes to here. Let us assume this is a 4500. Here we have 48. So this is the operand. So the address of the operand is given indirectly. That's why it is called register indirect addressing mode. Next, auto incrementer or decrementer. Auto increment or decrementer. So in auto increment, example is add R1 comma R auto. plus. So that means plus operator, it is represented after the register. So that means suppose if R auto is 4000, if R auto is a 4000, then it will go to this particular memory location, then it will access the data. So suppose in this location, if the operand is 35, so it will go to this address 4000, then the operand will be accessed, then the R auto address will be incremented to the next consecutive location. So next consecutive location is a 4001. So after performing operation, the content of R auto is equal to 4001. Similarly, auto decrementing. Auto decrement instruction is a add R1 comma minus R auto. So here minus operator is given before the register. So that means initially first decrementing will be takes place, and after that the operand will be accessed. Suppose if R auto value is 4001, so it will go to the 4001. Okay, then it's first it will go to the here 4001, then it will be decremented by 1, it will become, the address will be decremented by 1, it will become 4000, then this particular operand will be accessed. That is called auto decrement. Next, direct addressing mode. So direct addressing mode means the address of the operand is directly given in the instruction. Okay, so this is a direct addressing mode, LDAC 5. So 5 is the direct address that is given in the instruction. So directly go to that particular memory location, then we can access the operand. Then indirect addressing mode. So in indirect addressing mode, the address is not given directly. LDAC @4001. So 4001 is not the address of the operand. So 4001, it contains the address of the operand. So in that 4001 location, we will have a memory location, example 3500, which contains the operand. Next, relative addressing mode. So in relative addressing mode, the address of the operand can be calculated by adding the contents of the program counter with the address specified in the instruction. So here, so in this relative addressing mode, we are using program counter as one of the register. So in relative addressing mode, the effective address is calculated by adding the address by adding the content of program counter with the address mentioned in the instruction. So PC content is added with the address mentioned in the instruction, so that you will get the effective address. So from that effective address, we are accessing the operand. Next, index address register. So in index addressing mode, it is similar to the relative addressing mode, except the registers used. So in relative addressing mode, we are using program counter, but in the indexed addressing mode, we are using index register. That means SI, source index, or the destination index, plus the address specified in the address part of the instruction, so that you will get the effective address. Next, base register addressing mode. So this is base register addressing mode. It is also similar to the index addressing mode, except the register. So in index addressing mode, we are using the registers as SI or DI. But in the base register addressing mode, we are adding the content of base register BX or BP plus the address specified in the instruction. After adding, we will get some address. So that will be the effective address of the operand. So these are the various types of the addressing modes. So in this lecture, we have discussed about the definitions and terminology of the CPU and the computer arithmetic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.